characterized say, in remembering something, or they're couched at the level of constituents of the mechanism, which may be far too low to give a coherent account of the mechanism itself. Nonetheless, much of contemporary psychology is very engaged in the project of trying to understand mechanisms responsible for memory recall, visual perception, etc. Okay, so let me give a counterpoint to this perspective that has been pursued by many as an alternative to thinking in terms of mechanisms. And in this part, I'll use Tony Shimero as my foil, since Tony is eagerly pushing that a dynamical systems perspective ought to be viewed not as compatible to mechanistic explanation in grants, in many cases they are, but as an alternative. And a kind of way of approaching dynamical systems approach to mechanistic, or to cognitive phenomena is that which is exemplified in Scott Kelso's work on coordination dynamics. Many of you have encountered this kind of task paradigm that Scott has used as an exemplar, where try moving your fingers either out of phase with each other, like windshield wipers, or in phase with each other, and as you speed up the frequency of the motion, the anti-phase movement breaks down and is supplanted by the in-phase motion. And what Scott has wanted to do then is actually to give us a mathematical characterization of this phenomenon. So how the relative phase of the motion is related to an order parameter that gives us a potential function. And what he will show you is that, in fact, there are regularities created by this function, particularly if you look at the relation of the two coefficients A and B here. As that ratio of the ratio of A to B changes, the attractor landscape, basins in which you can get stable behavior, changes. So with the ratio set at 1 to 1, you have two basins of attraction, both in phase and anti-phase are stable attractors. Notice that they're bottoms in the troughs, but any space in between is unstable. But as that ratio changes, about here, the second attractor has disappeared, leaving us with just one basin of attraction. And for Kelso, understanding this relationship and the kind of changes that imposes on the attractor structure is sufficient to explain this example of coordination dynamics and a whole host of others for which the same mathematical equation suffices. And the thing to think about in this framework is that it's a focus on things like order parameters and the mathematical relations, not parts and operations of a mechanism that are being invoked to explain the phenomenon. Advocates of this approach, such as Shimero, want to emphasize also that from this perspective, one should be looking for, this is actually a figure for Andy Beer, but one really should be looking not just, say, into the nervous system to understand the phenomena, but one's looking at the integration of activity within the brain, within the body, within the environment, so that we end up talking about closely coordinated perception and action, and the idea then that change over time is going to be characterized in a set of magnitudes that can be captured in differential equations. And what Shimero wants to emphasize is this inquiry proceeds in developing explanations without any particular concern or any need to concern oneself with, say, what kind of mechanisms there might be in the brain that are underlying this kind of behavior. Moreover, and to bring this even into sharper focus, one of the objections that has been made by dynamical systems folks has been targeted at a notion that's very prominent in mainstream cognitive science, the notion of representations. I characterized the application of the mechanistic framework to cognitive science as involving information processing, where there are processes for manipulating representation. Tim Van Gelder, now 15 years ago, advanced the Watt governor as a new model or a landmark for models of cognition, which he offered as an alternative to the Turing machine. For those who have not ever encountered the Watt governor before, James Watt faced a challenge with the steam engine to develop a way of regulating the flow of steam so that the machinery in the engine would run at a constant rate. The problem would be that if any changes were made to the machinery that was running, say somebody took a bathroom break that was using one of the machines, all the other machines would speed up. And he needed a way of regulating the flow of steam coming into the engine that's driving the flywheel, regulating it so that the speed, the rest of the apparatus is downstream from this. The rest, that apparatus would run at a constant rate. What he devised was a system whereby a spindle was put on the flywheel, fly-out arms were attached to the spindle so that they would move by centrifugal force, and then a linkage mechanism so that if the engine was running too quickly, the arms would be pushed out further. The linkage mechanism would then close the valve very quickly to bring it back to the target speed. Similarly, if it slowed down, the linkage mechanism would lead to the valve opening. And what Van Gelder wanted to emphasize is that this kind of system performs its function without representation, as he said, given pretty much any reasonable characterization of representation, and he also glosses that as anything standing in for some future state of affairs. I'll come back to this example a bit later, but what I want to, because I would perversely will argue that there are representations in the Watt governor, but what Van Gelder wants to emphasize, similar to many other dynamicists, is rather what we need to do is characterize this whole system in terms of, turns out, two differential equations. This is simply one of them. This one relates the angle of the arms to omega here, which is the speed of the engine. And that once one has that kind of representation of what's going on in the Watt governor, one doesn't need to invoke representations within the Watt governor or any particular mechanistic account of the governor. Okay, so I've so far laid out the basics of the mechanistic approach to explanation, contrasted it with the dynamic systems approach. Now what I want to do is argue for the hybrid kind of approach. But to get at that, let me take as one of the now standard conceptions of mechanism, which I think is fatally flawed. And it's fatally flawed because it assumes that the mechanism is going to operate essentially sequentially. So Mockmer, Darden, and Craver in the 2000 paper characterized mechanisms are entities and activities, parts and operations, organized such that they're productive of regular changes, but here comes the linearity, from start or setup to finish or termination conditions. Now, I want to acknowledge that for many purposes, this is how biologists think about mechanisms. But in fact, what I will be emphasizing is that it's not adequate to many biological mechanisms, because biological mechanisms typically are not organized sequentially. And this makes a tremendous difference to how you need to think about and characterize mechanisms in biology. But this is extremely hard for the human brain. Evidence for that is just how hard it was for the human mind to get its head around the phenomenon of negative feedback. Negative feedback now is highly familiar to us, but it was first introduced in 270 before the Common Era in Xebius's design for a water clock. In this, what he needed to do was to get a design in which a float would move up steadily